Welcome to Math 31. This is a lesson on oblique or slant asymptotes, and this is going to be the final lesson of this unit. Sort of a small thing, but it is an interesting little topic, and it'll explain the behavior of some of the graphs we've been looking at so far. So to start it off, if you were to consider this function, y is equal to x plus 1 over x, and then have a look at the graph, this is what you end up getting. So nothing all that remarkable about it. It appears to be a hyperbolic type shape, but it is not. It is oblique. That is, it's not opening up vertically or horizontally. And then, if you were to consider a line, in this case, a line that's y of equation y equal x, you'll see that that thing goes right, or it behaves like an asymptote. In fact, it is an asymptote. It's a slant asymptote. So we could say correctly, that the line y equal x is a slant asymptote or oblique asymptote. So the function will be approaching that imaginary line, just not touching it. And if you went further with this, and just looked at this equation on its own, it probably wouldn't occur to you to do this normally, but if you did get a common denominator for these two terms, which would be x, this one would stay the way it is, and x times x is x squared. We get this. Now that's a different thing, different look, and in fact it does give us less information, but what you notice is the exponent, x2, is the leading exponent on top is 1 greater than the exponent of the leading term on the denominator. And that's the tip-off that we're going to get a slant asymptote. So in general, functions of this form, so any function where the leading exponent is x to the n, and then the leading exponent on the denominator is x to the n minus 1, that is 1 less, we'll have a slant asymptote of form y is equal to mx plus b. Now if you think back to regular horizontal asymptotes, that where we had been up until this lesson is if the numerator was 1 greater than the denominator, the exponent, we recognize that there was no limit as x increased or decreased without bounds. Therefore, there was no horizontal asymptote, and that's true. But in those cases, what you are getting, in fact, is a slant asymptote. Now, it's only true when the numerator is 1 greater than the denominator. If it's 2 greater, you actually get an oblique asymptote that's a parabola, which is another story. But the other thing is recognizing what it is. Like if we have the equation in this form, the simplified form, then the equation is given to us. So we know it's y is equal to x. So let's go through a few. So the equation of the slant asymptotes are the following. First off, this one. This one doesn't require any work. And we take the linear part of the function. So what you should get is a linear, and then you should get a rational part. And the linear part is the slant asymptote. So therefore the equation is going to be y is equal to x plus 1 is the slant asymptote. And that's basically it. Let's take a look at the graph. That's what the graph looks like. And then if you put the line in, y is equal to x plus 1, you can see that it appears to be an asymptote. So what you're probably wondering, okay, fine and dandy, if I'm in that form, I can tell what the slant asymptote is. What if it is not in that form? So that would be of this style. So to express in the proper form, and so I'll make a note here, this is not a very technical illustration of it, but to express in form y is equal to mx plus b plus a over x, use long division. Because what you're getting through division, you're getting a quotient. And then you're getting a remainder. So if we divide this out with long division, we'll then get it in the form where the linear part will be extracted, and then whatever is left for a remainder will just be the remaining part, which doesn't have any effect on the slant asymptote. Of course, it does affect the graph itself, but not the asymptote. So with care, we take the x squared plus 1, and we divide it by x plus 1. Now, as you will remember, you need to take these ones and include all the missing terms. So x squared plus 1 must be written as x squared plus 0x plus 1 divided by x plus 1. And of course, it's the leading terms that dictate things, so x times x is x squared. Multiply the x by the 1, so that's plus 1x, and then subtract. So x squared minus x squared is 0. 0 minus 1. Always be really careful with that subtraction operation. 0x minus 1x is negative 1x. Carry the 1 down. X times negative 1 is equal to negative 1x. So we get negative 1x minus 1. And then when we subtract, well, negative 1 minus negative 1, the signs will change. It becomes plus. And then and it's gone, of course, and then 1 minus negative 1 is 2. So the remainder is actually equal to 2. So the form of this equation could be written as the quotient, which is x minus 1, plus the remainder of 2 over top of what you were dividing by, which is x plus 1, over top of the divisor. And that means the slant asymptote is y is equal to x minus 1. So that's all you have to do. Now we take a look at the graph itself, and then the asymptote drawn in, and that's what we'll see. Let's do one more, and I think that should probably take care of any variations that you're likely to encounter in the next little while. As always, feel free to pause me and do it on your own. But here we go, x cubed. Now, we have to make sure all the terms are there. So 0x squared plus 0x plus 0 divided by x squared plus 0x plus 1. So x squared times x times x is equal to x cubed. We multiply each of those terms in. That'll give us x cubed. 0x times x, of course, is going to be 0x squared. X times 1 is going to be plus 1x. And then subtract. So x cubed minus x cubed is 0. 0 minus 0 is 0. 0 minus 1x is negative 1x. And then plus 0 if you want to bring that one down. And you can see now that we don't even have a remaining term or to divide into. So the form that we would get if we put it into the linear form would be the quotient of x and then plus the remainder is negative 1x or negative x over the divisor, which is x squared plus 1. Now this could also be written, if you wanted to, as x minus x over x squared plus 1. Now if you ever had any doubt whether you did it right or wrong, all you do is get a common denominator. So to check, find an LCD. And that will take you right back where you started from. But the slant asymptote, in this case, is y is equal to x. And let us also look at the graph. This one's a little more interesting just because of the nature of the second part of it, the rational part. So your graph isn't quite as good to look at, but the asymptote would go like this then. So we actually do approach it in a slightly different way. But we still have the slant asymptote. Is it useful? Well, it can if you take the time to find it, which truthfully most people don't bother. If you do take the time to find it, though, it does make the graph a little bit easier to draw. But you have so many other tools to draw these, turning points and points of inflection, that sometimes they don't seem as useful. So that's it for this lesson. Thank you for your time.